Good afternoon, everyone. We continue today from where we stopped in last lecture. In last lecture, we were solving for the magnetic field at the point P. We did part A, and now we'll continue with part B. For part B, we need to calculate the magnetic field due to the whole two wires, not only those small elements of the wires. So we will solve now for the magnetic field coming from those two wires. As we saw, we have two infinite wires. One of them has a current I'm calling I1 equals to 12 ampere. The second one is I2 equals to 24 ampere. The point P right here that I am using as the center of my coordinates. I have X, I have Y, and I have Z. So I have two infinite wires. So if I am to calculate the magnetic field at the point P, I know that the distance between the two wires is 5 centimeters, and the distance here 2.5 centimeters, which means the magnetic field at the point P due to the current I1 is mu naught I1 divided by 2 pi R1, where R1 is 2.5 centimeters and R2 is also 2.5 centimeters, which means the magnitude B1 was to 4 pi 10 to the power minus 7 times 12 divided by 2 pi times 2.5 10 to the power minus 2, which means B1 is 9.6 10 to the power minus 5. And the direction now. The direction B1 is, if you take the right hand and use the right hand rule, where the thumb is the direction of the current and your fingers are curling toward the direction of the magnetic field. In this case, the magnetic field at the point P will be pointing minus K hat. How did this happen? Well, I'd like to remind you that the magnetic field will be perpendicular on the plane that has the vector and the differential element. So the differential element is, as you can see here, is part of the wire, and the wire is a straight wire, and this wire is sitting in the XY plane, and the point of interest P is also sitting in the XY plane, which means that the magnetic field should be perpendicular on the XY plane, and that's why right at this point B1 will be in the negative direction of Z. What about the second magnetic field? The second magnetic field is going also, the thumb defines the direction of the current going from the right to the left, right? Then the magnetic field will be going into the screen as well at P. So that's why if I am to draw the magnetic field direction for P2 coming from I2, it will always be pointing into the screen. And in this case, P2, P2 is due to the current I2, and this is exactly what I wanted to say. B2 is twice the current B1 because the distance is the same and the current is twice, which means that B2 in magnitude equals to 2 times B1 in magnitude. Why? The only difference here in magnitude would be, instead of a 12, it will be 24, and that's why B2 in magnitude equals to 19.2 10 to the power minus 5 Tesla. And we said that B2 as a vector equals to 19.2 10 to the power minus 5, and the direction again based on the right hand rule going from the right to the left, then it will be curling the screen. So this one would be minus k hat as well. Yes, same direction. The total magnetic field, since both are in the same direction, will be B net equals to B1 plus B2, or B net will be 9.6 to the power minus 5 minus k hat plus 19.2 to the power minus 5 minus k hat, and B net equals to 28.8 10 to the power minus 5 minus k hat. Yeah, we talked about that. Opposite direction for two wires that are in parallel will lead to a constructive magnetic field in between. Constructive magnetic field in between. Okay, now the last part of the question, which is part C. Part C says if we cut those two wires right at the point P, where basically we're taking half of those infinite wires, how much would be the magnetic field at point P? Now, due to the symmetry, due to the symmetry, if I am to cut those two infinite wires right here, and I only consider the left part, of the wires, where this one is still I1 equals to 12 ampere, and I2 equals to 24 ampere. In this case, due to the symmetry, the magnetic field will be half of the magnetic field achieved in part B. So the B net nu will have the same direction, however, it will be 28.8 10 to the power minus 5, same direction, minus k hat, Tesla. So this means that if my magnetic field for the infinite wire is over 2 pi r, then half of the wire at the same point of interest will be half infinite wire will be mu naught I over 4 pi r. Where did we get this one from? If you recall, when we did the calculation for the magnetic field for a finite wire from minus A to A, we found at this point in the center, at this point of this in the center where it was a distance of x, we found that the magnetic field equal to mu naught I over 4 pi. Then this one was y over x for y squared plus x squared from minus A to A. This was the magnetic field that we derived for a finite wire sweeping the y from minus A to A, if you recall. Now, what happens if I sweep my wire? If I sweep my wire now, this is half. If I sweep my wire, instead of from minus A to A, I sweep it. When I swept it from minus infinity to infinity, I got this. Now, if I sweep it instead from minus infinity to infinity, I swept it from 0 to infinity to represent half of an infinite wire. Then in this case, I will be substituting y with infinity. Then this one will be mu naught I over 4 pi x. And now this one would be infinity over infinity minus 0. So the whole thing leads to 1. And the magnetic field for half of infinite wire right at the point of the middle equals to 4 pi x, and x can be substituted also with r, so this can be also called mu naught I over 4 pi r. So this is the magnetic field for a half infinite, which basically means a very long wire. However, I'm cutting it right at the middle, and I'm only considering half of it. So the first point, the point of interest is right at one end of the wire, and the other one is an infinite wire. Any question before we continue? Okay. So let's move on to the next slide. In this slide, I just want to uh, reiterate on the differences in uh, a straight wire when we find the magnetic field for the straight wire, and a loop. Or part of what I want to say is, if I have a straight wire, we're taking the thumb as the direction of the wire, right? If we have a straight wire, we take the thumb as the direction of the wire, and then the fingers will give me the direction of the magnetic field that is circulating around this straight wire. One point I want to stress on here again is the direction of the magnetic field. If I have a wire that has a current, I goes into through this wire. And I would like to find the magnetic field right at the point P and at the point Q. One of them is, as you can see, above the wire, and the second point is below the wire. So this one is a Q and this one is P. What is the direction of the magnetic field right at the point P? So both of them are on the X, Y. So the point Q and point P are in the XY plane. What are the direction of the magnetic field? What are the directions of the magnetic field at the point P and point Q? Minus K for Q. Okay. Well, okay. For Q, it will be out of the page. Yes. For Q, it will be out of the page. Why? If you take your thumb, direction of the current, and then it will be curling out of the page for Q, and for P, it will be into the screen. So this is extremely important that you know the differences. This is all based on how are those magnetic fields circulating around that wire. So if we have the straight wire, we said that we take the thumb as the direction of the wire, and the fingers will give me the direction of the magnetic field. Now, if I am to bend this wire, you see that the magnetic field will follow those bends till I make them as a loop. And in this case, the magnetic field will continue make those circular shapes around the wire, but because now I made it as a loop, right on the axis that goes through the center of the loop, the magnetic field will be perpendicular on that loop, will be right perpendicular on that loop. Now, what happens if I move closer to the loop physically? Then the magnetic field will start curving, such that he makes also those circular field lines, such that it goes from the north toward the south. And notice that right here at this point, it will always be, as we will see later on, but keep this in mind, that right at those points in the line that goes through the loop, it will be tangential to that circle, which basically means it will be perpendicular in the loop. We will be using this one later on, but just keep this one in mind for one single loop. But how do we get the direction of the magnetic field? If we have a loop that has a current going through that loop, then this time we take the fingers in the right hand also. The fingers are as warping in the same direction that the current is going through. However, this time the thumb will be pointing to the direction of the magnetic field. So if I have now the current entering from the bottom wire going up to the top, coming back through the top, this means that it will be curling this way, and this one is the direction from left to the right. And this is how we calculate, or we relate the direction of the magnetic field to the direction of the current in a loop. So if we take a cross section of that loop, basically looking from one side of the loop, I'm looking here such that the current is entering from the bottom, going back out of the screen from the top side of that loop. This is what I was just referring to earlier, that the magnetic field right at on the axis that goes through the center of the loop will be straight. We'll talk about that later, and once we come to the equation of the magnetic field due to the loop. But once you come closer to the side of that loop, you will see that the magnetic field will start curving, because at the end they want to make the magnetic field as a closed loops, closed paths. So this means I have two directions, as we have seen before. As we have seen before, if you look at this area, which is the loop itself, you will see that the magnetic field is going from left to the right. However, if you look at the outside area up here and down here, you will see that the magnetic field is entering, going from right to the left, which is opposite than this direction. This means if I am to look at on top of the loop, just from the top of the loop, what I can see that the magnetic field inside this loop will be out of the screen, pointing out of the screen, and the magnetic field outside the loop will be pointing into the screen. Let's look at this question where we're asked to find the north magnetic pole of this current loop. So if you want to find the magnetic pole, the north magnetic pole, this means you need to use the right hand rule in order to define the direction of the magnetic field. If you have the current entering from the top, leaving out of the screen from the bottom side, then this means that the magnetic field should be pointing from the right to the left. To me, this looks from the right to the left, which means which point would be the location of the magnetic of the north magnetic pole? It will be the point D. Yes. Draw the lines for the field, then the magnetic field would look like this. I have posted under the simulations a YouTube video about the 3D visualization of the magnetic field lines. Have a look at when you have time. I will be posting more materials about the loop, the magnetic field due to the loop and due to the what's called the solenoid later on. So if you recall, this is how we used to calculate the magnetic dipole moment. We used to use the right-hand rule where the currents are curling toward where the fingers are curling toward the direction of the current, and then the thumb will be pointing to the direction of the magnetic dipole moment. And we said that this is equivalent to a bar magnet, and this is the magnetic dipole moment of the bar magnet is in the same direction, which means that the north would be up and the south would be down. Now let's look at magnetic field equation for a loop. If we have the loop uh, aligned on the XY plane, then I need to calculate the magnetic field right on the z-axis, where the z-axis is going through the center of the loop. And the current, as you can see, is rotating as shown in the figure with the radius of A. We need to calculate the magnetic field right at the point, at the red point here, red dot here on the z-axis. Now, if we assume that the differential element is right there at the top, this means that the distance or the displacement vector between this differential element and the point is this. So in this case, the magnetic field, the differential magnetic field coming from this DL would be perpendicular on this line. Let me call this one DL1 and this one DL1 and this one DB1. So I have magnetic field perpendicular right on this line. Why is it going this way? Well, look at the direction of the current. Direction of the current means, take the direction of the current means it will be pointing in this direction. Only that DL, only this DL will result into a DB1 that is perpendicular on the displacement vector between DL1 and the point, the red point here, which I'm calling P. Now, if I take a second differential element in the same direction, I'm calling it DL2, at the symmetrical location against the plane of symmetry or line of symmetry here. This one would be DL2. And in this case, this one would be R2 if this is R1. This one is R2. This is going to result into a DB1 that is also perpendicular on R2. DB2. Now, this DB1 is due to DL1. This DB2 is due to DL2. If I want to find the total dB, the total differential magnetic field due to dl1 and dl2, it will be those components will cancel, and those components on the z-axis will add. So I only have one component of the magnetic field, which is on the z-axis. Now remember, this is only for two differential elements that are mirrored against the xz plane. Now, if you take all the pairs, you will always end up canceling the magnetic field on the z-axis, the same as what we have seen here, and adding the magnetic field along the z. In this case, the only component of the magnetic field will be on the z-axis, and the equation would be given as this. This is the magnitude of the magnetic field due to a loop at an elevated point of z. B loop equals to mu naught I over 2 a squared. A is the radius of the loop, divided by a squared plus z squared to the power 3 over 2. Now, what happens when I want to calculate the magnetic? So this is right here. The magnetic field will be pointing in this direction. So this is the B loop. And the B loop is given to me by this equation. Now, if I want to calculate the magnetic field right at this point, it will also be in this direction. However, by substituting z with 0, the B loop at point P will be mu naught I over 2a, where this whole thing becomes 1 over a. So now we have two equations for the magnetic field. I did not go through the integration. We'll leave this one. So we're not going into the integration. I just wanted to explain to you why the magnetic field for a loop right at any point on the axis that goes through the center of the loop is always perpendicular on that loop due to how we explain the magnetic field, taking a pair of a mirrored pairs with two differential elements that are in the opposite directions, rotational wise in the same direction. But at the end, the magnetic field at any elevated point, any point right on this axis, is given by mu naught I over 2 a squared over a squared plus z squared to the power 3 over 2. And right at the center of the loop will be mu naught I over 2a, where a is the radius and z is the distance from the loop. Now, at the end, you have a magnetic field that is a function. That is a function? Let's take, for example, this magnetic field for the loop. at the center is to 2 mu naught I over 2A. So at the end, you have a ratio here between I and A. And as you can see, the ratio here is linear with the magnetic field and proportional with the current and inverse proportional with the A. As long as you maintain an equal ratio between the current and the radius, you should be getting the same magnetic field, for instance, right at the center of the loop. So after we then it's not a loop. Then it's not a loop. Okay, so after introducing the magnetic field due to a wire, an infinite wire, and the magnetic field due to a half of an infinite wire, and then we introduced the magnetic field at the center of a loop, I will use the same symmetry approach to find the magnetic field of a half loop. So in this case, if I said that the magnetic field if I said the magnetic field for an infinite wire was mu naught I over 2 pi r, and then the magnetic field for half infinite wire as mu naught I over 4 pi r. Then we just found that the magnetic field for a loop is mu naught I over 2a. Then the magnetic field due to a half loop should be mu naught I over 4a. All this due to the symmetry. We've seen how did we do that for the first case after we have done the integration. Then for the second one, we stopped right at introducing only the equation, and then we used the symmetry to find half of the loop. So now if I take this approach as pieces of those wires, and I try to find the calculate and try to calculate the magnetic field due to different uh, shapes of those wires, I can apply the superposition approach to calculate the magnetic field, as long as I am calculating the magnetic field right at the same point. So in this case, if we want to apply the superposition to calculate the magnetic field right at the point P due to this shape, we have an infinite wire coming from left and then curving in a semicircular shape, and then going back. I am interested to calculate the magnetic field right at the point P. How do I do this? Well, let's do this together. If I have that wire, and then I have the point P here, and I have the current I going in this direction, while the distance here is R, and it is the same as the radius of this semicircular shape, and then I have the same also R. Then how can I calculate the magnetic field right at the point P using the superposition? This may be looking as a complex shape, but it can be decomposed into three distinguished wires or segments. So if I'm to now delete this, take this as a point P, then if I come and cut this wire right from here, then I can get three shapes of wires that all are contributing to the magnetic field at the point P. The first one would be a half infinite wire, where I have the wire all the way coming point P with a current I, plus I have a loop, a semicircular shape at P with the radius also R. I need to calculate the magnetic field at that point, and then plus the last one, which is P is up, and this wire is like this. So the distance here is R, the distance here is also R, and this is the point P. We have the current going in this direction. So as you can see here, I have now three distinguished sections of wires that I can use my uh, earlier derived half an infinite wire and semicircular loop to calculate the magnetic field right at the point P. So let me start with, this is the B1, case 1, giving me B1. This is B2. This is B3. So far, I did not talk about the directions. I'm only going to talk now in the beginning at the magnitude. So I have B1 equals to mu naught I over 4 pi R1. All of them have the same R. So in this case, B1 equals to 4 pi 10 to the power minus 7 times I. I is now given to me, divided by 4 pi R1. You will see that they don't cancel out. The top and the bottom, they don't cancel out. Just wait. Yes, they add. Remember, what did we say about two wires, parallel wires with opposite currents? the magnetic field inside will be between them will be constructive. But just give me a couple of minutes till I finish this. Then B1. So remember, what did we say here about the coordinates? Let me add the coordinates here. I have X, Y, and this is Z. So B1 equals to I over R1 10 to the power minus 7. And the direction is going minus K hat. Let's do B3 since we are dealing with the half infinite wires. B3 doesn't have the same direction. Let's see. For B3, if I have the current going this way, then the magnetic field will be going into the minus K hat as well. And the value would be the same. So this is R3, and as I said, R1 equals to R2 equals to R3. So I'll keep it R1, 10 to the power minus 7, and the direction will still be minus K hat. Now let's look at B2. B2 is a loop, semicircular loop. In this case, if you take your fingers as the direction of the current, then the magnetic field is going into the page, into the screen as well. And in this case, B3, sorry, B2 would be mu naught I over 4R B2 also minus K hat 4 pi 10 to the power minus 7 I divided by 4R minus K hat. So the total V, all of them are in the direction of into the screen. So I have I over 1 10 to the power minus 7 times 2, because B3 equals to B1. So I have 2I over R1 10 to the power minus 7 K hat minus K hat plus pi I over R 1 10 to the power minus 7 also K hat. So this is the magnetic field using the superposition approach to calculate the magnetic field right at the point P, where this point P happened to be right at the edge of the half infinite wires for both half, and also it happened to be the center for the semi-circular loop. Any questions so far? B1, we said that the thumb goes in the direction of the current. The thumb goes in the direction of the current, and then the fingers will curl, defining the direction of the magnetic field. we said that if we have a wire going in this direction, and I have, let's say, those 2 points, and I would like to count to know the direction of the magnetic field right at those 2 points. In this case, because using the right hand rule, the magnetic field at Q will be out of the screen, the magnetic field at P will be into the screen. For B2, again, for B2, because the current is curving, we take the fingers as the direction of the current, and then the thumb would be the direction of the magnetic field. Okay. Now, if I stack several loops on top of each other such that they are coming from the same wire with a tight wound, I will be getting what's called the solenoid. Yes, that's correct. So in this case, as I said, I will be getting a solenoid once I tightly wound this wire. Let's say if you do it on a pencil, you tightly, you will get what's called the solenoid, which are basically a stack of loops uh, right on top of each others. In this case, before I describe how is the field is going to look like in the solenoid, I would like to refresh your memory about that single loop that we've done. If you recall, we said that for the single loop, if I have the magnetic field right on the axis that goes through the center of the loop being perpendicular, the more I come closer to the side of the loop, the more curvature, the more I see curves, the more it curves till it, you can see those small circular curves, and right on this line at those points will be tangential, and they will be also perpendicular, however, in the opposite direction. So we talked about that. Now, if I have now 3 loops, what's going to happen to the magnetic field? Right at this, on the x-axis, the magnetic field will be, as you can see, will be constructive. There will be added all the components right on the axis that goes through the center of the solenoid. The magnetic field will be constructive and will be added. However, outside the solenoid, which I'm taking here the center loop as an example, we have seen that the B2, due to this loop, B2, due to this loop, which is in the center, is also perpendicular and pointing this way. However, because that point is tilted with respect to loop number 1 and loop number 3, you will see, and the direction of the magnetic field is in this direction, you will see, because this one is deflected, this one is going to come from the curve, from the other field lines that are curving this way. That's why at this point we can see that the magnetic field of B1 is pointing up in this direction. However, for loop number 3, they are also coming from those fields, and that's why, because the magnetic field isn't going in this direction, then it will curve. It is curving this way, coming back, and that's why this B3 is pointing tilted this way right at this point. Now, what's going to happen here is the projection of P1 on this will cancel with the projection of B3 like this, will end up adding on this axis. So B1, the projection of B1 will add in this direction, B1 and B3, and here on the vertical axis will cancel. But this is going to be close to B2, which means that the magnetic field right at this point will be close to 0. That's why if I look at the solenoid, I see the magnetic field is being concentrated right in the center of the solenoid. However, it will be extremely weak right outside the solenoid. So here, as you can see, the magnetic field here is very weak outside. However, the magnetic field is very well concentrated and strong right in the center of the solenoid. Let's take this example before we stop. I have, as you can see here, magnetic field in this solenoid going in this direction. What do you think of the current in this red dot? Out of the page. You are absolutely correct. Why is it out of the page? It is out of the page because if you follow the right-hand rule while taking the thumb as the direction of the magnetic field, then the current will be curling such that at the red dot, it will be pointing out of the page. So here will be a dot. So the correct answer is D, out of the page. Okay, so do you have any question before we stop? Okay, go ahead. Okay, go ahead. Anyone else has a quicker question to ask before your colleague finish his question? Oh, okay. Okay, I can post that. I can post that. You're welcome. Any other questions? Okay. Okay. That's great. So I'll see you on Friday. You're welcome. Have a good day. Thank you. See you on Friday. Thank you. You're welcome.